Previously, we've talked about inverse variation as products being equal, like this x1, y1 equals x2, y2. Another way to think about it is with inverse variation, the product is a constant. So instead of having one constant equal another constant, we could have, or the same constant, we could have that product equals some constant of proportionality or constant of variation k. We can solve this for y by just dividing both sides by x, and we get this equation right here, y equals k divided by x. This is a standard form for inverse variation. I do want to point out that frequently we do something called joint variation, where the relationship might not be so simple as y equals k over x. Like we could have y equals k over x squared, or y equals the square root of k times the square root of x for direct variation. So what matters is the form. This one on top is an inverse variation, and this one down here is a direct variation. It's just in this second case, y varies directly as the square root of x. And in this first case, y varies inversely as the square of x. So it's not limited to just y equals k divided by x, but that's the general form, is we're dividing by the independent variable. So let's do this problem. This says find r when t equals 6. So there's a situation that we don't know all of the parts. If r varies inversely as t, so that tells us our mathematical relationship, and r equals 15 when t equals 3. So that third part is the situation that we know. So situation unknown, mathematical relationship, and situation that we do know. For the mathematical relationship, if r varies inversely as t, we have r equals k divided by t. Now what we want to do here is evaluate this when r equals 15 and t equals 3, so we can find the k value. So we have 15 equals k divided by 3. To solve for k, multiply both sides by 3. We find 45 equals k. So again, we took our form, which we knew because r varies inversely as t. We evaluated the information that we were given to find our constant, to find our k value. And now what we're going to do is we're going to rewrite the equation with that constant of variation in it. In other words, this becomes r equals 45 divided by t. At this point, we could figure out, if we were given any t value, we could figure out that r value. This is the general model for this mathematical problem. And now we can use that model to answer the first question we were asked. Find r when t equals 6. So find r when t equals 6. If we have 45 divided by 6, r equals 7.5 if you like decimals, or 15 over 2 if you prefer fractions. This problem, though, is a little more boilerplate because we're given everything very nicely laid out for us. Let's do an application problem. So this problem says that the heat loss through rock wool, so we have heat loss through rock wool insulation, is inversely proportional to the thickness of that rock wool. If the loss through 6 inches of rock wool is 3,200 BTU per hour, find the loss through 2.5 inches of rock wool. We don't need to know what rock wool is. We do need to know that BTU per hour, that's a heat unit per hour, so that's our heat loss. So what we're told is heat loss is inversely proportional to thickness. So our mathematical relationship is heat loss equals K divided by the thickness. Let's write that as H equals K divided by T. Now, we're given a situation that we know. We're given that 6 inches of rock wool results in a heat loss of 3,200 BTU per hour. So we can plug that in for the H and the T in order to find the K value. 3,200 is our heat loss. K we don't know. T is 6. Multiplying both sides by 6, I found that 19,200 equals K. So our equation of variation has become H equals 19200 divided by T. From here, we want to find the heat loss through 2.5 inches of rock wool. So the heat loss would be 19,200 divided by 2.5. which works out to be a heat loss of 7,680 BTU per hour. Notice this is kind of what we would expect. A thicker insulation had less heat loss, and thinner insulation had a greater heat loss. Thank you.